Okay, so as I was saying, so if you're seeing something like that, it could come from, it could be seen as graphical problem, or it could be seen as data. So if there are some markings on the graph, then you might have to actually translate this into data, and so say, I don't know, if this is 5 and 3, and then this is 1, 2, and 3, and you have that xy data of the function 1, 5, 2, 3, and so on, and then deal with that data. So then in that case, what is the challenge of the computation once the transition has been made? And there is no challenge, because it's going to be followed by addition, subtraction, or division, some pure algebra. The challenge is that you actually to understand the concept. So if you see a picture like that, you got to know what Riemann sum is to begin with, or what the difference quotient is, or whatever this velocity, what the velocity is related to this, or displacement, or things like that. Rate of change. So those are a bunch of terms that are used interchangeably depending on the context. So that is the challenge, really, not the computational part. The computational part is what I was going to review first. Is the computational part, in an analytical sense, is manipulating formulas. So algebraic thing. So differentiation, like this. The product rule. So you need to remember certainly those formulas. So sum rule, constant multiple rule, product rule, quotient rule, and the chain rule, especially. So you can pretty much it's pretty much guaranteed that there will be something about the chain rule in the compositions on the final, one way or another. So that requires, in addition to knowing what's about, remembering and being comfortable using those formulas. So that's its own challenge, and it is a different challenge. So once again, this is pretty much the concept itself. That's the first one, the first example I have here. The understanding the concept is pretty much also almost the beginning and the end of the problem. If you understand it, you translate it in simple data and you solve the problem through some algebra. And so that's really not the second step is easy. Here, as I said, the challenge is multiple challenges, because it's like algebra that you know from before, but it's like on steroids. You may have noticed it. Because there are rules, just like in algebra. You follow them, religiously. So whenever you deal with whatever you've got, you do it following some of the rules has got to apply. So every step that you have to be more or less sure that you are using some kind of rule, because you cannot freely manipulate it. And the why with steroids is we're not dealing with numbers anymore. So it would be so easy if those x's and y's were just numbers, and you're dealing with x's and y's. You're just doing operations with numbers. These operations with functions. So remember that came up a couple of times. This is the input, an input function. And then once the computations has been carried out, what is it? Sine x plus x cosine x. This is the output function. So that is something very important to understand. It is, well, what is the meaning of differentiation integration? It is producing function from functions.
Would it be cosine x plus x sine x?
X sine x. No. 1, right? I differentiate x first, it's 1, and then multiply by the function which I do not differentiate, so it's sine. Right, and on the second try, I leave the first function alone and differentiate the second one. Okay, so that is the challenge. However, so with all the steroids thing, you should not forget that still the algebra and the still rules apply, and still what you're doing is you're making a bunch of statements. That came up yesterday. Remember, Gavin was writing something, and he was clearly knew what he was talking about, but he just didn't write it the way it's supposed to be. It is, you're making statement, you got to make sure that the statements that you make are correct. So even though you mean well, you have to also write what you mean. And so if two things are equal to each other, you say that they are with the sign. If they are not equal, well, maybe then you have to either switch to words. Sometimes, sometimes when you have solving equations, especially, that the transition from one to the next is not equality. So you have x squared plus 1 is equal to 0, then you switch to this one next. These two equations are not equal to each other. So this step is not, you're not saying that these two are equal to each other. So then that's the challenge of solving equations, that you have to actually, there's nothing but to do but to insert some words into this. Unfortunately, I don't see a lot of words used in writing. And so then that's projects in part should make you deal with that, but you have to say something like if, then, or whatever the language you want to use, but you still have to know what is that you're trying to accomplish. And solving equations is also manipulating formulas in a way that would preserve, if things were equal to each other in the first equation, they still should be equal to each other in the second equation, something like that. And that is the logical sequence of steps that takes you to the end, hopefully. Okay, so that is the differentiation. That's a chapter. The chapter about differentiation is about this. So formulas, like 6 or so, and producing new functions. It is very technical, and frequently you see tests of calculus that consist nothing of but these formulas. Okay, so why? Because, well, they are challenging enough, and they are easy to test for. However, whether the concepts are being understood, that's a different issue. And so I try to have kind of spread it out, the problems that we face in a variety of things. So for example, the sum rule, constant multiple rule, it seems like we're using them for these kind of computations. I just did, right? So I used no, actually I didn't use. I used the product rule, but they are. They just like rule of algebra. They have some very practical, or rather common sense ideas behind it, and they might pop up in a situation that are not necessarily just like this very straightforward situation. There is a hierarchy of importance, however, and that is in those, how many? One. So sum rule, constant multiple rule, I'm talking about differentiation number 3, product rule, quotient rule, and the chain rule. Okay, so actually the beginning and the end, these are most important ones. This is called collective linearity. Linearity rule, or linearity condition rule, is also a misleading statement, because it suggests that you just have to follow the rules and that's the only purpose. But it's like law of nature. So sometimes you call, instead of R, you can put L there. Some law, constant multiple law, because that's how the universe operates, apparently. And so we're looking for patterns. So I'm trying to right now look at the big picture, and I hope that's what probably you should do as you're getting ready for the final, is in spite of all this kind of sequential development that we've had of this class, and logically we're building this theory little by little, but now you're done with that, and hopefully you have some kind of holistic view of it. So like you got like a bird flying over, or, well, that's one metaphor. Another metaphor, we have building a house brick by brick, and now it's built, and now we want to live in it. So it doesn't really matter at what point brick was laid, each brick. We are just living in it, and hopefully it is good enough for us to have a roof over our heads. Okay, so I don't want to go specifically into these. Just once again, the warning is that the naive, a specific word that is used for these, the naive product rule is not correct. So the product, the derivative of the product is not equal to the product of the derivatives. The same with the ratio, even though it is true for the sum rule. So the derivative of the sum is equal to the sum of the derivatives. Replacing the sum with the product it's not all right anymore. Well, that's just the way it works. Okay, so geometric meanings behind all these formulas are something for us to contemplate as an extra reasoning behind why this is true and this is not true, something like that. Okay, so so I'm not going to bother you on the final with something complex. I don't know if you have you ever used like help forums for calculus? Well, there I monitor. I use Facebook, and there are help forums on Facebook, and so if I just sometimes I read, sometimes I help, but the problems are sometimes they are primarily of this kind, but way more complicated. Okay, so either integrate. Well, first of all, there are 3 times more integration than differentiation to begin with, because that's way more challenging, which you refer primarily to the beginning of calculus 2 rather than calculus 3. But they are very computational, and the formulas might be they're just overwhelming. So I certainly have no interest in that. For a number of reasons, it's really counterproductive. But you have to be comfortable with formulas that maybe just a tiny bit more complex than that. So the algebra won't overwhelm you as long as you know the formula. The formula, you plug it in 1-2 lines of computation, you should be done with it. Okay, so nothing more than that.
So could there be an instance where there's 3 rules and 1 problem?
Well, let's see. Like I said, these two are, at some point I just stopped paying attention because they're just so simple and obvious kind of, and so natural, so you don't really you should give them a second thought. These are more complex, and I'm going to tell you that it's unlikely to have a differentiation with only 1 rule applied. Beyond 2, it's possible, but maybe most of the time 2, 3. It shouldn't be a big deal. It's just every rule is just an extra line of your computation at most. So if you do it step by step, simplifying little by little, you're not going to be in any trouble. Except for the chain rule, that is just it is the biggest challenge. And if I give you the even if right now I ask you to differentiate sine x ln x squared. It's a composition of 3 functions in a row rather than 2. Okay, so that would be already a challenge. It is a challenge. It really tests your understanding of the chain rule, but I do feel that it's probably all calculus probably you will be still feeling a little bit shaky about it. So I don't want to push it too hard. Derivative, second derivatives. So that could be another one. So even though the function is somewhat simple, such as the one that I have number 2 over there, but then what if you need to find the second derivative? Well, so you should know simply that the second derivative is the derivative of the derivative. Okay. So some patterns that we have seen are more than less to be remembered, but maybe a shortcut that, if you remember shortcut, you take it. If you don't, you are still okay if you just stick to the computation. So if you need a say third derivative of a quadratic polynomial, what's the answer? Yeah, it is, but actually quadratic, linear, it will be 0. Not just any constant, it will be 0. So the quadratic polynomial, you differentiate once, you have a linear. The second time it will be constant, and the third time that constant will be 0. Okay, so the pattern is if the number of differentiation is higher than the degree of the polynomial, then you will get a 0. It is a shortcut, but you might not remember it, so you just do it by hand and differentiate it, and so it will just take a little bit more time. remembering shortcuts is really not always productive. It's like you're driving, and if you take that drive every day and then you discover a shortcut, then you take it and you keep taking it. But if you are in a new place, you have a map. Just go with the map. You like if you take the shortcut, you might gain a couple of minutes. What's the point? You can get lost, and there's really no reason to. So if you're not sure, just stick to the very basic rules. So that's multiple sine. Remember, sine you differentiate 4 times, you get sine again. Things like that. Yeah.
That third example, would it be cosine of e times 1/2 square root x?
Square root? Where did you get the square root? Hold on, where did square root come from?
Wouldn't the squared turn into regular x, wouldn't it?
Well, one thing, you just, as soon as you identify the 3 functions, you got to differentiate them. So there would be then, but you don't know what the arguments are yet. So there will be cosine. The derivative of logarithm is what?
E.
No, 1 over derivative of logarithm 1 over that over. So if it is ln y, the derivative will be 1 over y. Okay, so it will be 1 over something, and then the x squared will be produced 2x. So that's right away you have. You like I said, you can do it one at a time and differentiate you put sine away and then deal with what's inside, and then you put them together. Or you can just remember that no matter how long that chain is. So this is usually it's 2 chain of 2 links, and this has 3 links. No matter how many you've got, you will have that many derivatives to multiply. So I have derivative of sine is cosine, derivative of ln y is 1 over y, and derivative of x squared is 2x. Okay, so that's all fine, except what are the arguments? So what do I put here? What's the middle term? 1 over?
1 over 2x?
No. No, the 3 derivatives, we already have the 3 derivatives. It is still x squared. Not times, but in.
Cosine of ln.
Of the whole thing, yes. That's right, like this. So it's still 3 derivatives, but the variables are, whatever they are, they remain. So whatever inside of sine was will remain there. Yeah. And if for whatever...
Whatever's outside and whatever was inside, you keep the same.
Right. So this is that's a shortcut. Once again, if remember without the shortcut, how do you deal with the chain rule? You introduce intermediate variables, and then there would be no doubt. Then when you have 1 over y with y equal x squared, then there is no doubt that I'm sorry, not 1 over y, ln y. Then there is no doubt that what your derivative is. It's 1 over y, and then you still substitute, because y is an intermediate variable. You got to get rid of it at the end, and you substitute, and you have 1 over x squared. Okay, so that's how the way you won't forget it, and that's the way I prefer to introduce it. But like I said, there are shortcuts, but they usually come up. You sort of come up with them yourself almost. When you do it a few times and you feel comfortable, then you realize that there's this little easy pattern that actually will make your computations way shorter. It just doesn't make sense to learn them, because the point of the formula is lost that way, and you just don't know where things come from. And the formula is more complicated. So it's easy to remember. I think it's easy to remember the derivative of the composition is equal to the product of the derivatives. That's the formula. That's the chain rule. So if you remember that, and as a starting point, and then you don't remember to introduce that extra variable, that you have a composition beginning and the end variables, but then there is one in the middle. So it's a consecutive computation. Okay, so it's a challenge. Functions that are differentiable but not twice. So remember, function that is continuous but not differentiable. What is it? Absolute value. Okay. And then the other one. Then since we are on this topic, function that is differentiable but not twice differentiable. I don't really want to expect you to remember, but I wonder if you know how to, if you don't remember, I presume, do you remember? Once again, differentiable, but not twice differentiable. I'm not even sure I ever brought it up, but you should be able to sort of construct it based on the knowledge that you have acquired since. So, and it has something to do with the absolute value. So absolute value is continuous, not differentiable. How do I build a function that is differentiable but not twice differentiable from this one?
Has to turn into it.
What?
The function in question, once differentiated, has to turn into its variable.
That's right. That's right. So the function that is, that's right. So we are looking then for a function. So this is, say, f. What I'm looking is for g, so that under the differentiation we'll get this function, right? So one single differentiation of that function that we're still looking for should produce function f, which is continuous but not differentiable, right? So if the derivative of g is equal to f, then g is differentiable, but it's not twice differentiable because f is not differentiable, right? Okay, so that I'm glad that this is understood, and then the question is, so how do we find g?
Would it be the absolute value formula taken to a power? Is that
No,
concept?
think about it. What I circled there is the answer. G prime is equal to f. What is g? Well, this is more recent stuff. Well, actually, this is something I've been trying to talk about from the very beginning. So if we know, and what we have been just talking about, if you know how to get from a function to its derivative, what are we trying to do now? From function g to its derivative f. And now we know f, and we want g. So what do we call this?
The integral.
Integral. So that's what g is. It's the integral of f. So then you end up integrating the absolute value, which is integrable, by the way, because it's continuous, so it's integrable. And then just imagine what if you could. Well, let's explore this function a little bit. So what if this is my absolute value and I start integrating? So can you imagine roughly what the graph would look like? Well, think about it. So f is equal to, or g prime is equal to f, right? So that's the problem that we have seen a few times, plotting. So this can be done either algebraically or graphical. Let's first graphically. Well, let's do simultaneously. Think about it. Remember, integration is happening separately from, you can do it separately on the two pieces, for positive values and negative values. So if I integrate that straight line over there, what do I get? This is y equal x.
Negative value.
What?
Constant negative value.
No, you're thinking differentiating, I think. Y equal x, what's the integral? Integral of x. In other words, is antiderivative, by the way. So what's the antiderivative of x? What is the function that you differentiate that you get x? Well, that's the thing about anti-differentiation. It's all based on your experience to make your life easier, and so that you don't have to think about those formulas of integration. In addition to formulas of differentiation, there are formulas of integration, and so that you don't have to remember those formulas. If you have had enough experience and you have differentiated enough times, you should be able to recall the situation when you differentiated a certain function and you ended up with a function equal to x. So something equal to x. What is that function?
X squared.
X squared over 2, but Close enough. So what it means that this will be the integral. Okay? Now let's move to the left, this one. The equation of this line is y equal negative x. If we integrate it, what do we get? So this one is y equal x squared over 2. What's the other one?
You just add a negative sign.
That's right. So it will be y equal negative x squared over 2, which looks like this. So it's a curve that looks a lot like the cubic function. The cubic function, it looks very similar. It is suspiciously similar, and but we know for sure that it is not it. So this is what the cubic pound y equal x cubed looks like, and it looks similar, but it's not the same function, right? It's made, that function is made of two parabolas, but it's not a parabola because parabola goes like this or like that. It cannot be split in the middle. So it's certainly not x cubed, and it is very smooth, which I don't think I gave it enough credit to being careful. It is smooth. There is a tangent line there. So by looking at it, you cannot tell whether or not, with a human eye, that's the way I see it, with a human eye you cannot tell whether a function is twice differentiable or not. Differentiability, remember, like with the absolute value, you see a cusp, it's not differentiable, right, the V shape. However, the second derivative, there is a tangent line there, right? It's the x-axis is the tangent line, and yet we just demonstrated that this function is not twice differentiable. So the picture doesn't really tell you that. I wouldn't worry a lot about that, but it is still a good exercise. So it is like those examples, the absolute value. Well, absolute value is a really important function to page to know it. But beyond that, there are some examples that just become so arcane and then just too complex to be worth. It's certainly not worth remembering. It's worth remembering the ideas behind them, or at least kind of incorporate them into your thinking, maybe even indirectly. And then, but the point of second derivative, that is certainly not anything arcane or unimportant. Remember, second derivative of your location is your acceleration. So if you speak of motion, then that's what it is. You differentiate your location or displacement, and you end up with the acceleration. That's the base of the whole Newtonian physics. Okay, so that might still come up. So I certainly expect you to remember that what I just said on the most basic level, right? So derivative of the location is the velocity, derivative of velocity is acceleration, and then antiderivative is walking backwards. Also, how you're gonna need if you do anti-differentiation, you need to find your location for velocity. You need to know your initial location. Otherwise, you have too much ambiguity here, right? Remember that infinitely many answers. Anti-differentiation produces infinitely many answers. Just as over here, I could have said like this, and it would be still a fine answer. This is what we did. We did anti-differentiation. In other words, for integration, but there are infinitely many answers. So it's hidden here. Whenever we have the integral sign, there are infinitely many answers there hiding. Okay, the chain rule, once again, I already mentioned the challenge. The decomposition is the main challenge, I believe. Okay, so remember it is behind why we care so much about the chain rule, besides just some kind of a complex formulas. Think about, I made up this formula, right? This one, I made it up just to make it complex, and certainly it wouldn't be worth it. But change of variables, change of units, that's what where compositions especially come into play big time. Okay, related rates and implicit differentiation. Okay, so So then, I guess worth mentioning the word problems that you may be facing. They're typically either about related rates or they're about optimization. Okay, they are not similar in any way. We'll get to optimization in a minute, hopefully. So related rates. What do you remember about related rates? The rate of change of what? But do you remember any example? The concept might be hard, so it's a good idea probably just to remember some kind of a one example that explains indirectly what the problem is about. So do you remember any problems, related rates problems? What?
Got the formula.
What?
Times quantity x minus h.
No, related rates. It's a term that is not exactly descriptive. It is related quantities, and then they have the derivatives that are related to, and then their derivatives are rates. Okay, so that's what it's about. So but why would we say related rather than just to say functions? That is the point. There is a point there. So why related? So we're talking about relations rather than functions. And the example is, in addition to some word problems, it is the problem what we might be talking about, something like this. X and Y are related, but they are not functionally related. Functionally related, you express one in terms of the other, or not. Okay, so this is implicit, this is explicit, and in either case they are related, but if you speak of related rates, they probably related but not explicitly express one in terms of the other. Okay, so that's what it's about. Very typical situation when you deal with in kind of applications or formulas, and you have a bunch of variables, and they might be like I don't know, h. Well, how about w squared times h? This is the volume of a box. Okay, with a square base. Okay. And height h. Okay, so then the question might be asked, suppose the volume of the box is changing in size, but not in volume. Okay, so say the volume is fixed, let's say 100, and then you end up with once again a relation between w and h that is fixed. So because there are no other variables involved. And then you might be asked to, if h is changing, what is going to be, how w will be changing, and vice versa. The problems that we did discuss were, remember, the radar gun. Okay, so the motion detected by the radar gun is this motion, how closer the car is getting to me, and how fast, even though the car is not moving towards me, it's moving sideways. And that is one quantity is that motion, and this is the other one. Okay, and so therefore they are related through the Pythagorean theorem, roughly. Okay, so this is the motion, and this is where I'm sitting with the radar gun, and this is where the other car is, and they are related to each other, and therefore their rates of change are also related to each other, and the rates of change of these two that we care about are the speeds. So the speed of the car, the actual that you care about, versus the speed of how fast it is approaching you by a direct line, they are related but not equal to each other. Remember that discussion? Remember what the conclusion?
They're proportional to each other?
I guess they are proportional. I can't remember, but they're proportional by a number that is not constant, though. So the conclusion is actually that it's the radar gun will always underestimate the speed.
Was that similar to the example with the tangential acceleration, stop sign that you mentioned? Fighting the speed ticket?
Maybe. Well, I'm not sure. Well, yeah, it is related. So we're talking about, so somebody is making a turn, And then on one hand, one quantity is that you are sitting in a car, and your location, that's one quantity. The other quantity is an observer. He's sitting here, and he cannot see where you are. He can only see and observe the angle. Okay, so the angle is the other quantity. These two quantities, your location on one hand and the angle on the other, are related, and therefore the rates of change also related, but in a kind of a non-trivial way. And so then, yeah, and it could be then looking at the angle only might be misleading, especially if there's as it was suggested by that guy, there's a tree here, and you cannot exactly see what happens when you at the very end of the turn, just when you made that turn. So did he stop at the stop sign? Well, even though he was covered by a split second there, well, you may have missed it because the angle is changing differently. You sort of expect it to move uniformly like this, and well, it actually deserves a separate analysis, and that link that I have somewhere does that. But this one is the same thing, but it is the mathematics has been distilled from a word problem. So there's x and there's a y, and there's a relation between them, and what you want to find is a dy dx without expressing y in terms of x explicitly. So you remember what we do with it to find dy dx? We think of y as a function of x without finding that function. We still think of the relation being functional, just implicit, and then we do differentiate with respect to x, so that there should be clarity about that. So 2x plus 2y, and then what? Dy dx. Okay. So because once again, it's always well, what does this produce? It's the chain rule again, right? There are more complicated curves, and but the essence is the same. So if you understand the simplest problem, it probably will get you through the rest of them. I don't think we discussed a lot the derivative of the inverse. So what we saw is y is equal to ln x, and x is equal to e to the y, the inverse, right? And then the relation between the derivatives is y is equal to 1 over x, x positive, and here it is dy dx, and this is dx dy is equal to e to the y. If you look at it on the surface, there is no relation between them. I mean, it is really quite remarkable that we actually made sense of there is a relation between them. So 1 over x on one hand and e to the y on the other hand. Okay, so what is the relation? And the answer is it's what it is. If you just do a substitution. Hold on a second. Where is that? Yeah. E to the y. Yeah. So where's so you just you get just to substitute one into the other, and it should work out. Why doesn't it work? Hold on. Why doesn't it work out? 1 over x is 1 over e to the y. Okay, I need to express it in terms of why do I? Yeah, and then you flip it upside down, because remember where the flip comes from. So that's another thing that you might be facing is a graphical kind of problem, is the finding the inverse with the graphically. So the graph is given, you have to remember to do that flip. Remember the flip? So if this is the function, what does the derivative look like?
Is it flipped over the origin?
No. Over what? As you remember? If it is about the inverse, then x and y got replaced, interchanged rather. So x becomes y becomes x. So how do you implement that? How do you carry out that operation? You have a piece of paper, right? So this is x, this is y. So this should be pointing that way, and x should be pointing this way. How do I make it happen? Right? So once again, the vertical should start pointing to my right and to your left, and vice versa. So I have to, so my right two fingers in my right hand should now be located where my two fingers in my left hand are. And the only way is to do this. So as you can see, what's happening? It's not a rotation. It's not a rotation through any angle. It's not a flip like this. It's not flip like that. It is a diagonal flip. Okay. So I flip about the x about y equal x diagonal this one. So then the graph will look like this. So this looks complicated, but actually probably a better idea is, since we are more interested in derivatives, then where is that comes from. It is, you probably can see it on a simple example. Where does that relation between the two derivatives comes from under this flip? You can imagine that you have one function like this, and the other one. So let's make them linear. It doesn't really matter. So let's make them linear, and because we're only interested in one point at a time, and one point at a time, and if we zoom in, then both graphs look like straight lines. So that's the kind of relation that you might encounter, and you can recognize. Do you see the relation between these two slopes? Rise, right? It's here, becomes run on one hand. On the other hand, the run becomes the rise, right? So the slope of the red one, slope of the red one is rise of the run, but the slope of the other one here is run of the rise. So which means that they are reciprocals. Okay, so that's roughly what we've got over here. The reciprocal, the derivative of each one is of one is the reciprocal of the other with the substitution. So you cannot see this. This is so simple because there are only two numbers to worry about. With functions, it's more complicated, but the rule still applies. It's the reciprocal, except you have to still carry out the substitution. So you have to. Otherwise, if you just take 1 over y and flip it, you have 1 over e to the y, but that doesn't help because you need to function in terms of x. So you have to substitute y is equal to 1 over e ln x, right? So once again, the derivative is 1 over, where is this? The derivative is e to the y, okay? Then I take its reciprocal, it's 1 over e to the y. Then I substitute x, I'm sorry, substitute y, which is ln x. I have e ln x, that formula, which is equal to what? 1 over x, that's right. So e and logarithm cancel each other, and you have 1 over x as promised. So that's the trip e to the y trip, and we have 1 over x. And we certainly can go backwards as well. Yeah?
I have a question about the previous example where it was x squared plus y squared equals 1. When
Yeah.
you have to simplify the answer, you got any further?
If you need to find dy dx, then yes. So if this is where you want to come, then it's usually, not usually, it's every single time. Let me just say that the algebra that you might encounter after differentiation might be complex. This is not the case. This one works out every single time. So if you are not unable to solve what you've got for dy dx, it means that you made a mistake somewhere. This one is certainly, you can see that dy dx is equal to negative 2x over 2y, right? It always works out this way because dy dx is always simply a multiple of something. So there won't be any kind of a, you won't encounter the square of the derivative. Because why? Because the chain rule. The chain rule gives the product of times the other derivative. And so it will appear only as a multiple, and which means that you can always factor it out and solve what's left. Okay, so like I said, if you're solving an optimization problem, as Gavin just did yesterday, remember he solved this problem with kind of a simplified one, and he had a beautiful answer suddenly, right? And then he went back to the kind of the originally the way he thought about the problem, and the function was more complex because you had 2 square roots. And when you differentiate, the formula becomes very unmanageable, and then it is practically speaking you might encounter very easily. But well, sometimes certain problems don't have this issue, like this one. Okay, so inverses, anti-differentiation, reversing differentiation, that's the whole thing to be remembered about anti-differentiation or integration is before we got to the Riemann sum, closer to the end, we did antiderivatives a little bit by simply reversing the direction. So certain formulas were read from right to left. So you do a differentiation from left to right naturally, and then you read it from right to left. That's anti-differentiation. So you know the answer, and you're looking for the question. That certainly is something of a challenge. Okay, so all right. Okay, so that's about differentiation. So now optimization problems. So it's still possible that you might encounter a word problem that is about optimization. So you, if so, then it probably will be split into 2. And so the first part is the translation, translating the words into mathematics without solving it. And then separately, problem might be you already have a function and you need to solve the mathematical part of the problem. So both of them are equally important, I suppose. I'm not sure which one is more important, but they're important. And usually it is the first one is more of a challenge because just turning words into mathematics is a challenge. So remember, the idea is, in my opinion, it is well, mathematics is, which is what I started with, is a bunch of statements. So every equation is in fact a statement with equal sign that stands for as. So it means that if you're reading, you can go backwards as well. So you take a formula, say x squared plus y squared is equal to 1. So you have a formula, you read it, and it is a sentence. Okay. I can even put a period here to emphasize that. Okay, but you can go backwards as well. So you have a English sentence, and as long as the participant in that sentence are some kind of quantities, then you can turn it into an equation. And without trying to solve the equation, without trying to figure out what it means or how to proceed, the translation part is what you usually call for, what is called for, and so you and the usual step is to name the quantities. So identify quantities, name them, and then take every sentence and replace words with those letters. And you have to really understand the algebra in order to do that, because sometimes they're hidden. So for you can imagine how many words stand for the for plus. It could be add or sum or together or something like that, and so it could be hidden and very spoken indirectly. But that is the link that links to mathematics, as it is abstract, to real life is language, and so the translation back and forth is crucial. And we are making things simpler. Turning things into mathematics makes it simpler rather than hard. Okay, so you can imagine that x squared plus y squared equal to 1. It can be described in a number of ways. and if it is spoken, it would be hard to deal with. But the equations are easy because we know what to do with them. Okay, so in this part, then those theorems that are important is for you to remember. Everybody pretty much remembers that, but I just want to make sure is that you remember positive derivative, roughly speaking, means increasing function. Okay, and the negative derivative, decreasing function, and then the things that trip people up is if derivative is equal to 0, then what does that mean? So f prime is increasing, then derivative is positive, then the function is increasing. When it is negative, the function is decreasing. What if derivative is equal to 0, then what?
It's not going anywhere.
What?
It's not going
What does
anywhere.
that mean?
It's a constant.
No, I'm talking about one point at a time. So let's say, so we just found a point where the derivative is equal to 0. What does it tell you about the function? It's a trick question.
It's not a function.
No, it's a function. What's the geometric meaning of? If in any doubt, then I'll look at the geometric meaning. Remember, the derivative is the slope of the tangent line. So all you're saying here is that the tangent line is horizontal. The slope is equal to 0. That's the horizontal tangent line. So that's the only thing that we can conclude. We would like to, foolishly, and that happens unfortunately all the time. So derivative equal to 0, and you conclude that it is a maximum or minimum, which is not true. So once again, an example should spring to mind. That shows that derivative equal to 0 is not necessarily mean that it's a maximum or minimum point. What's the example? Horizontal tangent line, but it's not a minimum maximum.
Photograph as a whole.
What?
Photograph as a whole, I think.
No, that's if there's a hole, it's not differentiable. It's not even continuous. So I gave you the tangent. Try to think of a function that has at 0, say here, this tangent, but it's neither maximum nor minimum. So not and not. What should it look like?
Would it be the 1 over sine x shifted to the left?
1 over sine?
Doesn't that go like this and
Oh.
flattens out?
Uh,
If you shifted it to the left, wouldn't it just have a tangent line equal to 0 at the origin?
it seems complicated. What? No, sine x times what?
No,
Or
1
sine
over sine.
x times sine this? 1 over sine x?
Yeah.
Like this? Well, it's undefined at 0.
That would flatten it out.
On all the way to the right, but I'm talking about one point. This is where my tangent line is. So you can have like a parabola that up, parabola down, and either both of them will have, one has minimum, the other have maximum. How do I produce that something that's neither? You saw this picture today. What's the formula? The easiest one. X third, yeah, right. So that should spring to mind whenever issue comes up. That this is the function that gives you an example that why you should not jump to the conclusion that I have over there. So this is the wrong conclusion. So it really doesn't tell us anything. Just as this one is even trickier because having the derivative positive really doesn't tell us anything, because the function, we can only make this conclusion about the function being increasing is only if the function, the derivative is positive on an interval. Just because the derivative is positive at one point doesn't really conclude anything. And once again, there are examples that show that it's not the case. I don't want to bother you with something that more obscure, but this one certainly is very, very important, and it comes up once in a while. So the theorems that you need to remember is that derivative equal to a positive on an open interval means that not at a point, but rather on an interval, say AB. Okay, then the function is increasing on that interval. Similarly, derivative is negative on an interval AB, then the function is decreasing. And then of course, if the function is equal to 0 on the whole interval, then it is simply a constant function. Okay, but it doesn't mean that the strategy of optimization that we have developed, and it relies on this very much, is wrong. It is a valid strategy, and the strategy is, remember, find all critical points of the function, which is the points where the derivative is equal to 0 or undefined, and then put them on a list and compare, plus the endpoints if you have an interval, and compare. Okay, so you realize that even though you have x cubed over there and you put 0 on the list, it's okay, because you know it will be discarded because there are bigger points. So if I'm talking about, say, to optimize this function on this interval, and by mistake, it's not really a mistake, I put the 0 on the list because the derivative is equal to 0 there. I don't want to check whether it is or not minimum maximum point. I'll just compare the values of the function at these three values, at these three locations, and I will be fine. So for example, this -1, 0, and 1. So f of -1 is -1, f of 0 is 0, f of 1, that's my list, is equal to 1. I compare the values, and then I declare that this is a max and this is the min, and this one is gone because of that. So the strategy is fine. So it's okay to have some extra values if you are planning to discard them. So that's pretty much what Fairmont Theorem is that if you have a maximum, then the derivative is equal to 0, but not vice versa necessarily. Okay, so those are theorems optimizing things here. Minimum, maximum. Sine and cosine have a bunch of maximum points, but only one maximum value, which is 1. Okay, the mean value theorem. So, if you don't, do you remember the mean value theorem, anyone, or at least the idea of it?
The mean value?
Yes.
Is it like adding all the values together and then dividing them by how many you had?
Dividing by what?
How many, say...
You're talking about the mean value of, if you have a bunch of values, how you take its mean, and that's how you do it. It is related, but not exactly. So the picture that you should have in mind is this. Hope you remember. So the mean value is the mean value of, how should I put it? Well, does this picture look familiar? So the mean, the mean is standing for the most part average. So average rate of change over an interval is the difference of the two values, f of b minus f of a, over b minus a. Okay, so the mean is in certain applications, including statistics, for example, is usually, it refers to quantities, like a list of quantities, and then add them together and divide by by the number of them, right? But even in statistics, the version of statistics that actually relies on calculus, that's how they do the mean. You take well, that's not how they do the mean. This is how they do the mean, and so did we. Mean or average value of f over the integral ab. Do you remember this? You integrate the function over the integral and then divide by the length of the integral. That's what the mean value means, and that's what they use in kind of a more advanced probability and statistics. And they match. You can imagine that that you sort of approximate your function with the bars, remember, and then there are n of them, and you divide by n. It will be pretty much the same as dividing by the length of the integral. Okay, I think I'll stop here, and we'll just then I'll just see you Monday, unless you have anything else you want to any question that you want to ask.